Hi everybody. Today we're going to go a little bit deeper into our uniform circular motion topic by talking about centripetal acceleration and centripetal force. So our objectives for this lesson are to define centripetal acceleration and centripetal force, and then to be able to solve some problems using centripetal acceleration and force. So before we get going, let's ask ourselves a question. If we have an object moving in uniform circular motion, we know it's moving at a constant linear speed, but does that mean that that object has constant velocity? Well, remember that velocity and speed are related, but velocity includes direction information that speed does not. So in order for an object to be moving in uniform circular motion at a constant velocity, not only would it have to have that constant linear speed, but it would always have to be moving in the same direction. And hopefully you realize anything that moves in a circle is certainly not moving in the same direction all the time. But let's see if we can figure out in what direction the object is moving at any one time as it moves around the circle. So let's take an example. Say you took a rock, you tied it to a string, and you spun it around your head at a nice constant speed. You would have your rock going around your head. What happened if the string broke at any one instant? Well, if that's ever happened to you know that the rock sort of flies off that circular path in the direction it was almost going at that point. What we find is the direction that the rock is actually moving is tangent to the circular path. Remember that a tangent line touches a function, or in this case a circle, at only one point. So our tangent line here, at that instant when the string broke, goes this way, and we would find that that's the direction that our rock would continue moving if the string broke. So that must be the direction that the rock is moving the instant before the string broke, and so that's the direction of our velocity at that point. But what we want to realize is the direction's constantly changing. So let's just look at a quick simulation to show us how the direction of that velocity is always changing as the object moves around the circle. Okay, so here we have an object in circular motion, and if you watch it as you go around, you can see that even though it's traveling at the same speed, the direction of the velocity is always changing, but that velocity is always tangent to the circle. So that answers our question. Does the object have constant velocity? The answer is no. And that's simply because the direction is different at every instant on the circle. So as a result, velocity changes. If you remember all the way from the beginning of the year when we started talking about velocity and how we can change velocity, we said that we can change velocity a couple of different ways. If we were moving in a straight line, which is what we did mostly for the first semester, we weren't changing direction. The only way we could change our velocity was by changing our speed, going faster or going slower. But we also said the way we can change our velocity is simply by changing our direction. And that's what we're doing here. We're moving at a constant speed, but our direction is constantly changing. So as a result, our velocity is changing. And if we have a changing velocity, we must have an acceleration. So the acceleration of objects that are moving in uniform circular motion is called centripetal acceleration. It's still represented with the letter A, but in this case it has a small subscript of a C just to indicate that it's a centripetal acceleration. Centripetal acceleration is found by squaring the linear speed, all right, whatever you're given in meters per second to how fast the object is going, divided by the radius of the circular path. Now the word centripetal means center seeking, and that means that centripetal acceleration is always directed towards the center of the circular path, because remember, acceleration has direction too. So when we talk about objects moving in uniform circular motion, you want to remember that the direction of the acceleration, the centripetal acceleration that's experienced by the object, is always directed towards the center of the path. Let's look at a quick example just to make sure we're okay. So we have a test car moving at a constant speed around a track. We know the radius of the track, and we want to know what is the centripetal acceleration of the test car. So what do we have? We know that the linear speed is equal to 19.7 meters per second. We know that the radius of the circle is 48.2 meters. And we know that our equation for centripetal acceleration is the linear speed squared divided by the radius. So we take our 19.7 meters per second, we square it, divide it by our radius. Alright, that gives us a number of 8.1. And let's just check our units. On the top, we would have meters squared over seconds squared, because we square every term in there, and that would be divided by, oh, got the meters there, divided by meters. If we take one of these meters, cancels out one of those meters, and we end up with units of meters per second squared, which is exactly what we expect for an acceleration. Okay, now, if you remember Newton's second law, F net equals ma, tells us that if we have an acceleration, we have to have a force causing that acceleration, or vice versa. The force that causes the centripetal acceleration is called the centripetal force. Again, it's represented with an uppercase F, just like any other force, but it has a lowercase c to let us know that it's a special type of force, the centripetal force. It's still equal to ma. In this case, a is the centripetal acceleration. So centripetal force equals mass times centripetal acceleration. Sometimes you're not given the centripetal acceleration, but you're given the linear speed and the radius. So what we do is we substitute the equation for centripetal acceleration right into this equation, so that we can also say that centripetal force equals the mass times the linear speed squared divided by the radius of the circle. Newton's second law tells us that a net force and the acceleration that it causes, or vice versa, are always in the same direction. So our net force is going to be in the same direction as our acceleration, and since our centripetal acceleration is directed towards the center of the circular path, so is our centripetal force. So you always want to remember that if we're talking about anything in uniform circular motion, the object experiences an acceleration and a force, both known as centripetal, and they are always directed towards the center of the circular path. Let's give ourselves another example real quick. We have a car moving around a track again at a constant speed. We know the radius of the track, and we want to know the magnitude of the centripetal force. So again, we have our mass of our car, 905. Right? We know that the linear speed is 35 meters per second. We know the radius of our circular path is equal to 3.25 kilometers. And I'm hoping that you're getting better at realizing that everything has to be in those standard metric unit measurements of meters, kilograms, and seconds. So we got to get rid of these kilometers, convert them into meters. There's 1,000 meters in every kilometer. So this is 3,250 meters. All right, our centripetal force. I don't have the value of centripetal acceleration, but I do have linear speed and the radius. So I'm going to use the substituted equation right out at the beginning of my solution. So I'm going to take my mass, 905 kilograms, times my linear speed squared. Don't forget the square. A lot of people do. Divided by the radius of the circular path, 3,250 meters. Alright, so our centripetal force is equal to 341. We should expect newtons, our units of force, but let's just check our units over here. We have our mass in kilograms. Our linear speed squared is meters squared divided by seconds squared. And when we divide that by the meters that are on the bottom, meter cancels out one of those. We end up with kilogram meter per second squared. F net equals ma. That is a Newton, so we know that we're okay. All right, let's try one more just to solve for one of the different variables. So here we have a pilot flying a plane in a circular path. We know the radius, we know the linear speed, but now we know the centripetal force. And we know it's a centripetal force, even though it doesn't directly say it in the problem, because it's saying a force needed to maintain circular motion. So as soon as you see that, you know that that means centripetal force. And it wants to know what is the mass of the pilot. So what do we have? We have linear speed equals 30 meters per second from our problem. We know the radius of our circular path is 100 meters. We know the centripetal force is equal to 635 newtons. And we're asked to find the mass. Well, we know that centripetal force equals MAC, but because I'm given linear speed and radius, I'm going to use this equation that already has that centripetal acceleration substituted. That would tell me that through a little algebra, mass is equal to the centripetal force times the radius divided by the linear speed squared. Substitute all my values. 635 newtons, 100 meters, and my linear speed squared. That should give us a number of 70.6. Since it's a mass, we should expect kilograms, but let's check our units just to make sure. A Newton is a kilogram meter per second squared. Right, multiplied by the meter on top, divided by a meter squared over a second squared. These guys cancel out. A meter times a meter is a meter squared, so they each cancel out with that, and I'm left with kilograms. So I confirm that my units are correct. Okay? The one thing I want to sum up about centripetal force, though, is I want you to realize it's just a force needed to maintain circular motion. It is not a new type of force. The forces that we learned about in the beginning of the year, applied forces and contact forces and field forces. Contact forces, applied, normal, tension, friction, those types of forces, and field forces, gravity, magnetic, and electric. They are still the types of forces that exist. Centripetal force is just a special type of net force. It's a summed up force caused by a sum of those types of forces we've already learned about that just keep an object in circular motion. So please do not think that it's a new type of force. It's simply a net force, just like F net equals ma, that causes an object to stay in circular motion. So we like to give it its own special symbol, that F sub c, to let us know our motion is circular.